Assalamu alaikum. I welcome you all in another lecture of fluid mechanics ME-2303. Continuing from the last class, we will be discussing some fluid properties in this class, and we will see the mathematical relation related to the properties of the fluid mechanics fluid. We will be discussing in the future class. Now let's see some fluid properties for the analysis of fluid behavior. So one of the most common and important fluid properties is density. Since you all know that density is the ratio of mass and volume, so this is quite elementary. There's nothing new about density in this lecture, so we will be covering it really quickly. Usually we represent density by rho, this symbol rho. The dimensions are ml minus 3, since kg per meter cube and kilograms is m and meter cube is l minus 3, right? So the units are, this is an SI unit, and you have slugs per feet cube, which is a British unit. Important thing is that density varies. It is not a constant, but it varies with the temperature. So for liquid and for gases, the variation in pressure and temperature has small effect on the rho, while in gases the pressure is significant. हम इसका मतलब ये है कि अगर आपके पास gases हैं तो variation जो है density का with respect to temperature and pressure वो significant होता है, whereas in liquid temperature pressure बढ़ाने से या कम करने से density के ऊपर ज़्यादा असर नहीं पड़ता. फॉर इंस्टेंस अगर आप गौर कीजिए, यहाँ पे एक एग्जांपल है कि 16 डिग्री फ़ारेनहाइट और 15.6 डिग्री सेल्सियस के ऊपर जो डेंसिटी है पानी की वो अप्रॉक्सीमेटली 999 किलोग्राम पर मीटर क्यूब या 1.94 स्लग्स पर फीट क्यूब है. इस ग्राफ के अंदर एक बात शो हो रही है कि अगर वाटर की डेंसिटी अराउंड 1000 है एट 4 डिग्री सेल्सियस, वाइल अगर आप टेम्परेचर बढ़ाते हैं तो डेंसिटी जो है वो कम होती है. इट्स इनवर्सली प्रोपोर्शनल. If you increase the temperature, the density decreases. You can see that here that even if you increase the temperature to 100 degrees Celsius, the density is decreasing to 960 kilograms per meter cube. So it's not a very significant change. Whereas this difference can be quite significant in case of gases. अगर आप ये गैस के लिए ग्राफ देखते हैं तो you will observe that the density of the gases significantly change as you increase the temperature or as you vary the pressure. Moving further, हमारे पास next property जो है वो specific weight है. This is another property which you have covered in your previous classes, for example thermodynamics. Specific weight is basically the weight per unit volume. It means that how the weight is being distributed across the whole body. So अगर आप इसको we represent the specific weight with the symbol gamma, and the units are Newton per meter cube, since it's a weight which is a force and volume is meter cube. The dimension of the gamma is basically the same dimensions of force per volume or Newton per meter cube. Pounds is a unit of force in British system, and meter cube can be replaced with feet cube. And the formula for gamma is rho gamma equals to rho g, where rho is the density and g is the acceleration due to gravity. Usually for example in case of water at 60 degree Fahrenheit, 15.6 degrees Celsius, the rho of water is approximately 1000, whereas the g is 9.8. So you can see that 9.8 into 1000 gives you 9.8 kilonewton per meter cube, or 9.8 exponential 3. So this is the gamma value, or usually these are the commonly used values in the analysis of the fluid mechanics. So these values, for example in the case of British unit, this is 62.4 pounds per pound per feet cube, and in case of SI unit this is 9.8 kilonewton or 9.8 exponential 3 Newton per meter cube. This is another very important fluid properties which we will be using in our later classes. Moving further, specific gravity is another fluid property which actually is used to compare two different fluids. It is unitless, and it is the ratio of the density of two different fluids. One fluid is water and one fluid is the other fluid which you are dealing with. For instance, the symbol is Sg. It's a dimensionless quantity. There is no units because the density at the numerator is also a density, and denominator is the density of the water. So for example, let's see an example. In case of water, the density of the water it basically gives you an idea that which liquid is how much heavier than the water. So if this ratio is greater than 1, which means that liquid is heavier than water. In case of if the this Sg value is less than 1, it means that the density is smaller than the density of water at 4 degrees Celsius. Let's take an example: water and mercury. Mercury is a heavy metal. It usually exists in liquid state. The density of mercury is 13.6 exponential 3, whereas the density of water is approximately around 1000 kilogram per meter cube at 4 degrees Celsius. So when you solve this, you actually get that the density is almost 13.6 times heavier than the water. This is a schematic representation of this phenomena, this example, whereas the 13.55 unit is required to have the same to balance 1 unit of mercury. So this is actually the same concept which you covered in thermodynamics 1 or thermodynamics 2 and in your last semesters. So moving further, usually let's fluid properties. Another important thing in when we are dealing with gases, sometimes we consider them ideal or perfect gas. So the gases are highly compressible in comparison to liquid. Ideal gas law relates the density change with respect to pressure and temperature, where R is the universal gas constant. Here the same concept which you covered in your previous classes, so we can just quickly skip them, and we will not be using these gas law, perfect ideal or perfect gas laws in fluid mechanics, since usually it deals with the gases, and we will not be dealing in gases in this course. But these are important concept to understand, that if you are applying general gas equation to a gas which is a type of fluid, you have to consider some important factors. And there are some assumptions. So the R is a constant whose values are written over here for air, and it depends upon the molecular weight as well. The temperature in this equation should be in absolute temperature, which is Kelvin or Rankine. Moving further, let's talk about pressure. Pressure is usually the same. Pressure is again an old concept. Pressure is basically the normal force exerted by the fluid molecules or particles on a flat surface. So the formula for pressure is force upon area, and it is represented by a symbol P. And since the force is Newton and the area is Newton meter squared, so the units are Newton per meter squared. There is nothing new in this slide for you. The units of pressure can easily be calculated by replacing the dimensions of F and A. The SI unit for pressure is Newton per meter square, which is equals to 1 Pascal. Another very important concept to understand about pressure is absolute pressure. Major pressure relative to absolute zero pressure only occur in perfect vacuum. Usually the real pressure of any container, of any fluid in a container, is actually absolute pressure, whereas the gauge pressure is relative to the atmosphere. So which means that for instance, if I have to calculate the absolute pressure, that is the summation of P atmosphere plus P gauge, whereas P gauge is basically the real pressure minus the P ATM. For instance, I can give you an example. If you consider the example of a tire, when you are measuring the pressure inside the tire, the gauge value, the gauge of the pressure gauge gives you a value. That value is basically the gauge pressure. So that is not the actual pressure, because the actual pressure is the value which is shown on the gauge plus the value which is outside, which is P ATM. So this is the same concept which you covered in thermodynamics 1. Absolute pressure is the real pressure, whereas the gauge pressure is basically the P absolute minus P ATM. So you can see from this relation that P absolute minus P ATM will be P gauge. Atmospheric pressure is a constant value. It varies with height, which means that at the sea level, this is usually around 14.6 psi pound per square inch, and in terms of SI unit, it is 101325 kilopascals. So these are the constant values which you should remember. Moving further, This is the schematic of the concept which I was discussing about P absolute in P ATM. For example, in this case, P absolute is basically the summation of P gauge minus P ATM. So if you want to calculate P gauge, or if any gauge is giving you the value at gauge pressure, that is actually equals to the absolute pressure minus P ATM. Whereas we have another gauge which can find the P vacuum. P vacuum vacuum gauges are used in the case when the pressure is lower than the P atmosphere, which means the absolute pressure is lower than the P ATM. It doesn't mean that there is no molecule or there is no pressure, but negative pressure means the pressure in the container is lower than the P ATM. For instance, the atmospheric pressure is 14 psi, and in a container the pressure is let's say 12 psi. This is an example of a vacuum pressure. So to calculate the vacuum pressure, we have to subtract the P ATM and P absolute, so we can find it, right? This equation can be seen here. P absolute can be found by P ATM minus P vacuum for the pressure lower than P ATM, and for pressure above P ATM you use the simple relation of P absolute equals to P gauge plus P ATM. So these are the same concept, old concept. So let's move on. Another very important property which is new to this course and which you might not have studied in your previous classes is viscosity. Viscosity is basically a quantitative measure of fluid resistance to flow. It means that in the fluid particles, while the fluids are flowing, while the particles are flowing, there is a relative resistance between the layers of the fluid, and this property can be observed when if you observe two different fluids, for example honey, oil and water. You see that for example, if we drop identical marbles in water, oil and honey, water in the case of water, the ball will reach the bottom quickly as compared to oil and honey, which means that there is a resistance between the layers, which is not allowing the marble to travel easily. Another, beside this marble example, we can see that the viscosity can be observed if for example, if you are having a honey in a jar and if you're trying to pour it, it takes more time compared to water or oil, and if you pour it from the same jar. So this is basically the relative resistance of the flow. We denoted it with the symbol mu. The units can be found later. The dimensions I will discuss dimension later, because the formula for Newton's the Newton's law of viscosity states that tau equals to mu into du upon dy. This relation will be discussed in the following slides. So we will discuss in detail how this relation came into existence. Kinematic viscosity is nothing but the ratio of the absolute or dynamic viscosity and the density. It is this unit is new. The units are basically of dynamic viscosity are poise or dyne second per centimeter square, or in case of SI unit they are Newton second per meter square, and kinematic viscosity is centimeter square upon second. So we will discuss this relation in detail in the next slides, inshallah. So let's see the effect of viscosity. Temperature wise and pressure wise. So this is actually temperature is very sensitive to viscosity is very sensitive to temperature. However, in pressure it is mildly dependent. It means temperature की बदलने से viscosity में तब्दीली ज़्यादा आती है. The viscosity is highly dependent on temperature, whereas viscosity is not as much dependent on pressure. Interestingly, when you increase the temperature, the viscosity of the liquid decreases, which can be seen from this graph, that when you are increasing the temperature, the viscosity of oil, glycerine and water are showing a decreasing trend. On the contrary, when you are increasing the temperature, the viscosity of air and hydrogen, which are gases, is increasing. This phenomena can be explained by the fact that when you increase the temperature, the average kinetic energy of the molecules increases, which means that the randomness increases and the probability of colliding the molecules with each other increases, whereas in the case of a liquid, when the temperature increases, the bond between the molecules or the particles gets weakened, and that actually allows the fluid to flow easily. So this behavior is actually opposite in gases and liquid. The behavior of the behavior of viscosity with respect to temperature. We have some relations which can be through which you can find the viscosity of a substance of a fluid, which are Sutherland equation and Andrade equation. These are the equations which are temperature dependent, and C and S are empirical constants which can be found by experiments. Whereas the other equation is D and B are also constant and T is absolute temperature. These two formulas by Sutherland and Andrade can be used to find the viscosity and find the viscosity with respect to as a function of temperature. Moving further, viscometer is a device which is used to find the viscosity of the fluid. Actually, this is a very simple device used other sophisticated devices to find the viscosity. So moving further, now this is the important topic to understand Newton's law of viscosity. As you remember, I showed this equation to you, which is tau equals to mu du upon dy, which is Newton's law of viscosity. Now in this topic we will be deriving these relations. Now let's consider a situation in which the fluid is actually trapped between two plates. These two blue plates are showing, these two blue things or plates are showing the plates. In between the fluid is trapped, which is shown here. What is happening there? The bottom plate is fixed, whereas the top plate is moving with certain velocity, which is u. This P, which is an applied force, is applied which parallel or shear to the around the surface of the fluid, whereas this plate is fixed. So what happens that the plate velocity is capital U. So you can see this this is a plate which is fixed. There is a fluid in between these two plates. The upper plate is being applied upon by a force which is P, which is actually a shear force, and the U is the velocity of the plate. What happens due to there is a velocity gradient. Velocity gradient means the velocity is changing from the bottom plate to the from bottom plate to the upper plate. So this triangle actually is showing the velocity profile. It is 0 at the bottom since the plate is fixed, and this is called no slip condition, which means that the velocity or the particle is sticking to the surface, and the particles which are stuck to the surface are not moving. As you go upwards, the velocity is increasing, and as you move till this plate, the velocity of the particle is the velocity of the plate, because the last particle in this vertical length is sticking with the upper plate. So what is happening? This shows that if I draw a y axis on this figure, so this velocity u is a function of y, which means that u is the velocity of the fluid, is variable. It is changing with respect to y. So if this line is linear, so if you can see the velocity gradient can be represented by du upon dy. So if the velocity is changing linearly, we can write that the velocity, which is the velocity of the fluid changing in this direction, is equals to capital U, which is the velocity at the top, or which is the velocity of the plate with which the fluid at the top surface are moving, into y, which is the length in the y direction, and b is the thickness between these two particles to these two plates. So this is the equation of the velocity profile. Interesting. The easier way to understand this concept is, for example, if you consider it as on an xy axis, so this line is along y axis, and if I want to find the equation of this line, so if the origin is at this point where my cursor is showing, so this is passing through the point which is at origin 0 0. You can see that this equation is u equals to u y upon b plus c, that the y ordinate is 0 in this case. So here we have the relation for the very linearly. But if I want to find the velocity gradient, we can simply have this equation, which is u, and if I differentiate it with respect to y, I can get the rate change of velocity or the velocity gradient of how the velocity is changing along this y direction. You can, this equation, this figure is also important because the force which is applied P is basically equals to tau, which is the shear stress, times the area of the plate, upper plate. Now let's analyze the whole figure again. When you are moving, when the plate is being moved, plate is being applied a force P, what happens that there is a velocity gradient, and the particles which are away from this plate are moving faster than the particles which are at the nearer to the bottom plate. So you can see there is a triangle, there forms a triangle. The point A is the one vertex of this triangle, whereas the B is the original vertex, and B dash is the vertex, and is the point which is a bit far from the point B initially. So there is an angle formed which is delta beta, which can be found by the fact by the equation that if I apply the tangent delta beta, delta A is the distance between these 2 points B and B dash, and this length B, which is the distance between the plates, can be divided. So we have this relation. Now delta A is basically the distance covered by the particle from B to B dash, which can be found by this relation, because u is the velocity of that particle with which the plate is moving, times delta t, which is the time taken by the particle from B to B dash. So if I replace this relation here, I can find that delta beta equals tan delta beta is equals to delta A upon B, where delta A can be replaced by u delta t. Now since the angle is very small, so we know that the tangent of a small angle is the same angle, because for example tangent of 1 degree is equals to approximately 1. So this equation is this equation can be modified as delta beta. So as we know that delta beta is a function not only for force but also of time. Okay, which means that time is also a factor, which is delta beta is also dependent upon time. So we can easily say that if I divide this relation with delta t, I can cancel out this delta t from. So what we will be left with? Gamma dot is basically the strain rate. Strain rate means that angular change, which is delta beta divided by delta t. This is the strain rate, and from this equation I can find that the u upon b equals to, from this equation strain rate equals to u upon b, which is equals to du upon dy. Okay, so this gamma is basically the strain rate. Strain rate means the rate at which the angle is changing when you are applying a force P. Similarly, gamma is also equals to du upon dy, as u upon p is equals to from this relation, right? Moving further, we know that the shear force which is applied here is proportional to the rate of shearing strain. So first of all, rate means anything which is being divided by time, and shearing strain means the change of angle delta beta. So if I replace it from here, to we can find the gamma is equals to du upon dy. So this relation still is valid, which means that the shear stress is proportional to the velocity gradient. Higher the gradient, the higher the shear forces. So this is valid for all the fluid, but in case when you remove this sign of proportionality, you have to have a constant which is called mu, which is actually the viscosity, which means that this relation holds for all the fluids, but the quantity or the numerical values might differ. That the difference in numerical values can be explained by the fact that there should be something missing in the equation, right? So that missing part is a quantity which is represented by mu, that is the dynamic viscosity, and this relation is called Newton's law of viscosity. If you have any questions regarding anything which we have covered so far, you can ask me in the live sessions. We will be having live session to discuss any query or answer any query. So this is it for the video, and we'll be continuing in the next lecture, inshallah. Thank you very much.